Have you ever wondered what happens when a cosmic visitor from another star system decides to dance dangerously close to our neighboring planet? What if I told you that right now, as you settle into the gentle rhythm of this exploration, an ancient wanderer designated 3I Atlas is approaching Mars on a trajectory that could fundamentally challenge everything we thought we understood about interstellar objects and planetary safety? This isn't just another routine astronomical event that unfolds predictably in the sterile calculations of orbital mechanics. 3I Atlas represents something far more intriguing and potentially unsettling: the third confirmed interstellar visitor to grace our solar system, carrying within its nucleus the frozen chemistry of distant stellar environments that operated under completely different rules than anything our Sun has ever known. Unlike the mysterious cigar-shaped Oumuamua that puzzled scientists in 2017, or Comet Borisov that provided our first clear glimpse of interstellar ice in 2019, this new visitor exhibits characteristics that make even veteran astronomers pause and reconsider their assumptions about cosmic wanderers. And here's what makes this encounter truly captivating. 3I Atlas isn't simply passing through our cosmic neighborhood like a polite tourist following a predictable itinerary. As it approaches Mars, this interstellar traveler is creating scenarios that could range from the beautifully mundane to the catastrophically transformative. Tonight, as we drift through this peaceful examination of cosmic possibilities, you'll discover why some researchers are quietly discussing outcomes that span from routine gravitational ballet to events that could reshape our understanding of planetary vulnerability in ways that echo through human consciousness for generations. Before we begin this gentle journey through space and speculation, remember to like, subscribe, and softly tap that notification bell if you find comfort in exploring the serene mysteries of our universe while your mind prepares for restful sleep. Picture, if you will, the vast emptiness between stars, not truly empty, but filled with ancient wanderers that have been drifting through the cosmic dark for millions or even billions of years. 3I Atlas began its journey in stellar environments we can only imagine, around a sun that may have died long before Earth's continents took their current shape. This interstellar messenger carries within its frozen heart the chemical signatures of formation processes that occurred under gravitational and radiation conditions completely foreign to our solar system's experience. The discovery of 3I Atlas in 2024 by the Atlas Telescope System in Hawaii marked another milestone in humanity's growing awareness that the space between stars isn't the vacant void we once imagined. Instead, it's populated by countless cosmic refugees, objects ejected from their birth systems during the violent processes of planetary formation, stellar evolution, or catastrophic gravitational encounters that flung them into the galactic wilderness to wander indefinitely between distant suns. What distinguishes 3I Atlas from its predecessors isn't just its origin story, but its current behavior as it approaches the inner regions of our solar system. Unlike Oumuamua, which maintained an enigmatic silence throughout its brief visit, or Comet Borisov, which behaved largely as astronomers expected a traditional comet should, this latest visitor is displaying characteristics that invite both scientific fascination and subtle concern. The object appears more comet-like than its mysterious predecessors, developing the familiar coma of vaporizing ice and dust that creates the ethereal beauty we associate with these cosmic wanderers. Yet beneath this familiar appearance lies complexity that defies easy categorization. As 3i Atlas continues its approach toward the Sun, astronomers are documenting behavioral patterns that don't perfectly match the textbook descriptions of how interstellar comets should evolve during their brief sojourns through alien stellar systems. These subtle anomalies, while not dramatically alarming, create an undercurrent of scientific uncertainty that makes the object's close approach to Mars particularly intriguing for researchers who understand that the universe often reserves its most profound lessons for moments when our predictions prove inadequate. The timing of this encounter adds another layer of cosmic poetry to an already remarkable story, as 3i Atlas prepares to make its closest approach to Mars during a period when humanity's robotic presence around the red planet has never been more sophisticated or extensive. As we drift deeper into this cosmic tale, consider the delicate dance of gravitational mechanics that will soon unfold between Mars and its interstellar visitor. The closest approach, predicted to occur at a distance roughly equivalent to traveling from Earth to the Moon about 75 times, might seem comfortably distant by terrestrial standards, yet in the context of cosmic encounters, this represents what astronomers consider a remarkably intimate celestial pas de deux. Mars, our rust-colored neighbor, stands as humanity's next great frontier, a world we've been studying with increasing sophistication through an expanding fleet of orbiters, landers, and rovers that have transformed our understanding of planetary evolution, climate dynamics, and the potential for life beyond Earth. The red planet serves as our cosmic laboratory, a place where we test technologies and develop strategies for humanity's eventual expansion beyond our home world. In many ways, Mars represents our practice ground for becoming a truly spacefaring civilization. But Mars also exists in a state of relative cosmic vulnerability that makes encounters with objects like 3i Atlas particularly worthy of careful observation and thoughtful speculation. Unlike Earth, which benefits from a robust magnetic field that deflects much of the charged particle radiation streaming from our Sun, Mars lost its global magnetic field billions of years ago, leaving it essentially naked to cosmic influences. This magnetic nakedness, combined with an atmosphere that's roughly 1% as dense as Earth's, means that Mars responds to cosmic visitors in ways that can be more dramatic and potentially longer-lasting than similar encounters might produce at our home planet. The current fleet of spacecraft studying Mars, including NASA's Perseverance rover, the orbiting Mars Reconnaissance Orbiter, ESA's ExoMars Trace Gas Orbiter, and several other robotic explorers, represents billions of dollars of sophisticated technology and decades of careful planning. These mechanical ambassadors are designed to operate in Mars' challenging environment, but they were engineered with expectations based on the planet's normal cosmic weather patterns. An encounter with an interstellar visitor introduces variables that spacecraft designers couldn't fully anticipate, creating scenarios where our most advanced planetary exploration tools might face their first real test of adaptability to genuinely unprecedented cosmic circumstances. The gentle irony of this situation isn't lost on researchers who've spent careers studying Mars. Just as we're developing the technological sophistication to seriously contemplate human missions to the red planet, the universe delivers a reminder that cosmic environments can change in ways we're still learning to predict and understand. In the hushed corridors of mission control centers around the world, engineers and scientists are quietly running calculations that explore the boundaries between routine cosmic encounters and scenarios that could fundamentally alter our relationship with Mars exploration. The worst-case possibilities they're modeling don't necessarily involve dramatic Hollywood-style catastrophes, but rather subtle shifts in planetary conditions that could accumulate over time to create lasting changes in Mars' environment, atmosphere, or electromagnetic behavior. Consider the delicate balance that governs Mars' current atmospheric state. The planet's thin envelope of gases, primarily carbon dioxide with traces of nitrogen, argon, and other components, exists in a precarious equilibrium that has persisted for millions of years. This atmospheric system, while stable over human timescales, remains sensitive to external influences that could trigger cascading changes in atmospheric chemistry, pressure dynamics, or thermal behavior. An interstellar visitor like 3I Atlas carries within its nucleus chemical components that formed under completely different stellar conditions, potentially including exotic organic compounds, unusual isotopic ratios, or trace elements that don't exist naturally anywhere in our solar system. The introduction of even minute quantities of such alien chemistry into Mars' atmosphere could initiate reaction cascades that unfold over months or years, gradually altering the planet's atmospheric composition in ways that might not become apparent until future missions attempt to operate in conditions that no longer match our current environmental models. Spacecraft life support systems, atmospheric processing equipment, and in situ resource utilization technologies are all calibrated to work with Mars' current atmospheric chemistry. Changes to that baseline could render entire categories of planned technology ineffective or unreliable. But atmospheric contamination represents just one category of potential long-term consequence. Mars's electromagnetic environment, already complex due to its lack of a global magnetic field and the presence of localized magnetic anomalies scattered across its surface, could be influenced by charged particles or electromagnetic fields associated with 3I Atlas. These influences might be too subtle to detect immediately, but could accumulate over time to create persistent changes in how solar wind interacts with Mars' upper atmosphere, how auroral phenomena develop, or how charged particle radiation affects surface conditions. The implications extend beyond scientific curiosity to encompass practical concerns about the future of Mars exploration and eventual human settlement. As we drift through these contemplations of cosmic consequence, it becomes important to understand that the scenarios we're exploring exist in the realm of possibility rather than probability. The universe operates according to physical laws that generally favor stability and predictability over chaos and disruption. Most cosmic encounters, even those involving objects from other stellar systems, unfold according to well-understood gravitational mechanics without producing dramatic or lasting changes to planetary environments. Yet, the history of planetary science is punctuated by discoveries that reminded us how much we still don't know about cosmic interactions and their potential consequences. The late heavy bombardment that scarred the inner solar system billions of years ago, the impact that likely created Earth's moon, the cosmic collision that may have contributed to the extinction of the dinosaurs, all serve as reminders that the universe occasionally produces events that reshape entire worlds in timeframes far shorter than geological processes typically require. 3I Atlas brings unique characteristics to its encounter with Mars that distinguish it from the more familiar objects we're accustomed to tracking through our solar system. Its interstellar origin means it carries chemical signatures and physical properties that evolved under stellar conditions we can only study through theoretical models and spectroscopic analysis. The object's nucleus, forged in environments where radiation fields, gravitational forces, and chemical processes operated according to parameters that never existed in our Sun's neighborhood, might respond to solar heating and Mars's gravitational influence in ways that don't perfectly match our predictions based on solar system comets. The behavioral patterns that 3I Atlas exhibits as it approaches the inner solar system, the development of its coma, the evolution of its brightness, the characteristics of its outgassing, provide clues about its composition and internal structure. But these observations must be interpreted through theoretical frameworks that have never been tested against actual interstellar objects. We're essentially learning the rules of interstellar comet behavior in real time, using 3I Atlas as our primary case study in a field of astronomy that barely existed a decade ago. This scientific uncertainty, while exciting from a research perspective, introduces elements of unpredictability into encounter scenarios that would be straightforward to model if we were dealing with a well-characterized solar system object. The margin of error in our predictions grows larger when we're working with cosmic visitors whose fundamental properties remain partially mysterious. The spacecraft currently studying Mars represent humanity's most sophisticated attempt to understand another planet through robotic proxies. But they also embody the technological limitations and assumptions of their era. These mechanical explorers were designed during a period when interstellar visitors were theoretical curiosities rather than observable realities, and their operational parameters reflect the environmental conditions that Mars was expected to maintain throughout their mission lifetimes. The Mars atmosphere, thin as it is, provides the medium through which these spacecraft communicate with Earth, navigate using atmospheric drag for orbital adjustments, and conduct atmospheric science measurements that contribute to our understanding of planetary climate evolution. Changes to atmospheric composition, density, or electromagnetic properties could affect spacecraft operations in ways ranging from subtle calibration drift to more significant performance degradation that might shorten mission lifetimes or reduce scientific productivity. Consider the delicate instruments aboard Mars orbiters that measure atmospheric composition through spectroscopic analysis of how sunlight and radio waves interact with gases in Mars' upper atmosphere. These measurements depend on precise calibration and stable baseline conditions to detect the subtle variations that reveal information about seasonal changes, dust storm dynamics, and long-term atmospheric evolution. The introduction of unexpected chemical components from 3I Atlas could create spectroscopic signatures that contaminate or complicate these measurements, potentially requiring months or years of additional analysis to separate genuine atmospheric changes from instrument artifacts. Surface rovers face their own categories of potential challenge from an encounter that introduces unexpected variables to the Martian environment. The solar panels that power most Mars surface missions are calibrated for the current atmospheric opacity and dust deposition patterns that characterize normal Martian weather. Changes to atmospheric chemistry could alter how dust particles interact electrostatically with spacecraft surfaces, potentially affecting power generation efficiency, or creating new categories of operational challenge that mission planners never anticipated. Even the communication systems that maintain contact between Mars, spacecraft, and Earth could be influenced by changes to Mars' ionosphere, the electrically charged layer of the upper atmosphere that affects radio wave propagation. These effects might manifest as subtle changes in signal quality or more dramatic disruptions to communication schedules, depending on the magnitude and duration of any electromagnetic disturbances associated with the 3I Atlas encounter. As we continue our gentle exploration of cosmic possibilities, it's worth considering how the gravitational dynamics of the 3I Atlas encounter might unfold in ways that create subtle but persistent changes to Mars's orbital environment. While the direct gravitational influence of the interstellar visitor on Mars itself would be minimal given the distances involved, the universe has a way of amplifying small perturbations through complex interactions that can produce consequences far exceeding their initial cause. Mars exists within a delicate gravitational ecosystem that includes not only its relationship with the Sun, but also its interactions with its two small moons, Phobos and Deimos, and the periodic gravitational influences of other planets as they move through their orbital cycles. This system has achieved a stable configuration over millions of years, but stability in orbital mechanics often means that small changes can cascade through the system in ways that gradually alter long-term behavior patterns. Phobos, the larger and closer of Mars' two moons, already exists in a precarious orbital situation. This irregularly shaped chunk of rock, likely a captured asteroid, orbits so close to Mars that tidal forces are gradually causing it to spiral inward toward an eventual collision with the planet. Though this dramatic finale isn't expected to occur for roughly 50 million years under current conditions. The Moon's proximity to Mars makes it sensitive to gravitational perturbations that might accelerate or alter this orbital decay timeline. Even a minimal gravitational nudge from 3I Atlas, combined with the object's passage through Mars' extended gravitational field, could introduce small changes to Phobos's orbital parameters that accumulate over decades or centuries. These changes might not be immediately detectable, but could become significant over the time frames relevant to human Mars exploration. A slightly altered Phobos orbit could affect tidal forces on Mars, influence the planet's rotational stability, or create orbital debris if the gravitational perturbations destabilize the Moon's already stressed internal structure. The outer moon, Deimos, while less dramatically positioned than Phobos, could also experience subtle orbital modifications that change its long-term relationship with Mars. These changes might affect the gravitational environment that future Mars missions would encounter, particularly spacecraft designed to use the moons as gravitational anchors for complex orbital maneuvers or as staging areas for surface operations. Beyond the immediate gravitational mechanics, the 3I Atlas encounter presents scenarios where the interstellar visitor's passage could trigger or influence dynamic processes within Mars itself. The planet's interior remains geologically active in subtle ways, with ongoing processes that include seasonal polar ice sublimation, possible subsurface water movement, and the gradual evolution of magnetic field anomalies scattered across its surface. Mars's internal structure, while less geologically active than Earth's, still harbors processes that could be sensitive to external influences. The planet's core, partially molten and containing iron that generates localized magnetic fields, operates according to thermal and convective dynamics that have persisted for billions of years. External gravitational influences, while typically too weak to affect planetary interiors directly, can sometimes trigger responses in systems that are already near critical thresholds for change. The planet's seasonal cycles, driven by its axial tilt and elliptical orbit around the Sun, create annual patterns of atmospheric pressure changes, polar ice sublimation, and dust storm activity that depend on precise energy balances between incoming solar radiation and atmospheric heat retention. Subtle changes to atmospheric composition from 3I Atlas could alter these energy balances in ways that shift seasonal timing, modify dust storm intensity, or change the patterns of water vapor movement between polar and equatorial regions. These changes might manifest as differences in the timing or intensity of Mars' famous global dust storms, planet-wide tempests that can persist for months and dramatically affect surface conditions. Such storms already pose significant challenges for solar-powered spacecraft, but alterations to their frequency, intensity, or duration could require fundamental changes to mission planning strategies for future Mars exploration efforts. The subsurface water ice that exists across much of Mars could also respond to changes in atmospheric conditions or electromagnetic environments associated with the 3I Atlas encounter. This frozen water, preserved in the planet's soil and rock layers, represents a crucial resource for future human missions. Changes to its stability, distribution, or accessibility could affect the feasibility of planned technologies for extracting water to support human life support systems and fuel production on Mars. Perhaps one of the most intriguing categories of worst-case scenario involves the possibility that 3I Atlas could introduce chemical or biological contamination that persists in the Martian environment, long after the object itself has continued its journey back toward interstellar space. This scenario operates on vastly different timescales than the immediate gravitational or electromagnetic effects we've been exploring, potentially creating consequences that unfold over decades or centuries. Interstellar objects like 3I Atlas have spent millions or billions of years traveling through the galaxy, during which time they may have encountered stellar environments, molecular clouds, or even debris from other planetary systems. Their surfaces and interiors could harbor chemical compounds that formed under stellar conditions radically different from those in our solar system. Or they might carry trace amounts of organic materials that originated in alien planetary environments we can only imagine. When such objects approach the Sun and begin outgassing, they release not only the familiar water vapor and carbon dioxide we expect from comets, but potentially exotic organic compounds, unusual isotopic ratios, or even microscopic particles that contain chemical signatures of their interstellar journey. If 3I Atlas deposits even minute quantities of such materials in Mars's atmospheric system, these alien compounds could persist in the planet's environment for extended periods. Mars's thin atmosphere and weak magnetic field provide limited protection against cosmic radiation, which means that complex organic molecules can sometimes survive longer on Mars than they would in Earth's more chemically active environment. Alien organic compounds introduced by 3I Atlas might integrate into Mars's atmospheric chemistry or settle into surface deposits where they could remain detectable for years or decades. The implications for astrobiology research could be profound. Mars exploration has always been driven partly by the hope of discovering evidence of past or present life on the red planet. The sophisticated instruments planned for future Mars sample return missions are designed to detect subtle chemical signatures that might indicate biological processes. However, these same instruments could be confounded by the presence of organic compounds that originated from 3I Atlas rather than from indigenous Martian processes. Future astrobiologists might find themselves in the challenging position of trying to distinguish between chemical signatures that represent genuine Martian biological activity and contamination from an interstellar visitor. This distinction could require developing entirely new analytical techniques and reference databases that account for the possibility of alien organic chemistry in Martian samples. As we drift deeper into these contemplations of cosmic consequence, the electromagnetic dimensions of a worst-case 3I Atlas encounter begin to reveal their subtle complexity. Mars's electromagnetic environment, already unique due to its lack of a global magnetic field, could be influenced by charged particles or electromagnetic phenomena associated with the interstellar visitor, in ways that create persistent changes to how the planet interacts with solar radiation and cosmic particles. The red planet's current electromagnetic signature results from a complex interaction between localized magnetic field remnants, geological scars from when Mars possessed a global magnetic field billions of years ago, and the continuous stream of charged particles flowing outward from our Sun. This interaction creates a dynamic but generally predictable pattern of electromagnetic behavior that affects everything from radio communication with spacecraft to the formation of Mars' tenuous auroral displays. 3I Atlas, as it approaches and passes near Mars, could introduce electromagnetic disturbances through several mechanisms. If the interstellar object carries residual magnetic fields from its formation environment, or if its outgassing creates charged particle streams that interact with Mars' existing electromagnetic environment, these influences could create temporary or even persistent changes to how electromagnetic phenomena behave in Mars' vicinity. Such changes might manifest as alterations to the planet's ionosphere, the electrically charged layer of the upper atmosphere that affects radio wave propagation and creates the medium through which many spacecraft communicate with Earth. Even subtle modifications to ionospheric behavior could affect communication reliability, navigation accuracy, or the performance of scientific instruments that depend on precise electromagnetic measurements. The implications extend beyond immediate technical challenges to encompass long-term questions about Mars' electromagnetic evolution. The planet's current electromagnetic environment represents a delicate balance between solar influences and local geological factors. External perturbations could potentially trigger changes that persist long after 3I Atlas has departed, creating a new electromagnetic baseline that future missions would need to accommodate. These electromagnetic effects could prove particularly challenging for the sophisticated radar systems and communication networks that future human missions will depend on for navigation, resource mapping, and maintaining contact with Earth during the complex operations required for establishing permanent settlements on Mars. The temporal aspects of potential 3I Atlas effects introduce another layer of complexity to our worst-case scenario considerations. Unlike the immediate and obvious consequences that might result from a direct impact or catastrophic atmospheric disruption, many of the most significant long-term effects could unfold so gradually that they might not be recognized as consequences of the interstellar encounter until years or decades after the event itself. Mars operates according to cycles and processes that span multiple timescales simultaneously. Daily temperature variations, seasonal atmospheric changes, periodic dust storms, and longer-term climate evolution all proceed according to different rhythms that interact in complex ways to create the planet's overall environmental behavior. The introduction of new variables by 3I Atlas could influence any or all of these cycles in ways that might not become apparent until sufficient time has passed for pattern recognition. Consider how subtle changes to atmospheric chemistry might gradually alter the planet's energy balance over multiple Martian years. Mars' thin atmosphere means that even small modifications to its composition could affect how efficiently the planet retains solar heat, how dust particles behave during storm events, or how water vapor moves between different regions of the planet. These changes might manifest as gradual shifts in seasonal timing, alterations to regional climate patterns, or modifications to the frequency and intensity of global dust storms. The challenge for researchers monitoring these potential effects lies in distinguishing between natural variations in Martian climate, which can be substantial even under normal conditions, and genuine changes triggered by the 3I Atlas encounter. Mars's climate system exhibits considerable natural variability that reflects the complex interactions between atmospheric dynamics, seasonal ice sublimation, dust storm cycles, and solar radiation patterns. Detecting subtle trends that might indicate 3I Atlas-related changes would require years of careful observation and sophisticated statistical analysis. Future Mars missions, particularly those designed to support human presence on the planet, would need to account for the possibility that environmental conditions might be slowly evolving in ways that weren't anticipated when mission systems were designed. Life support technologies, atmospheric processing equipment, and resource extraction systems all depend on assumptions about environmental stability that could prove inaccurate if 3I Atlas triggers gradual but persistent changes to Martian conditions. The cascading effects of a worst-case 3I Atlas encounter could extend far beyond Mars itself to influence humanity's broader relationship with space exploration and planetary protection. The psychological and institutional consequences of discovering that interstellar visitors can significantly alter planetary environments might prove as transformative as any direct physical effects on Mars. The modern space exploration enterprise has been built on assumptions about cosmic stability that allow mission planners to design spacecraft and plan operations based on predictable environmental conditions. If 3I Atlas demonstrates that interstellar objects can introduce unpredictable variables to planetary environments, future space missions might require fundamental redesigns that account for the possibility of encountering conditions that differ from historical baselines. Planetary protection protocols, currently focused on preventing contamination between worlds within our solar system, might need expansion to address contamination from interstellar sources. The discovery that alien chemistry or electromagnetic phenomena could persist in planetary environments for extended periods would require developing new sterilization techniques, monitoring systems, and international agreements that govern how we respond to interstellar contamination events. The economic implications alone could be staggering. The aerospace industry has invested billions of dollars in developing Mars exploration technologies based on current understanding of Martian environmental conditions. If 3I Atlas effects require significant modifications to life support systems, atmospheric processing equipment, or communication technologies, entire categories of space technology might require costly redesign and revalidation. International space cooperation, already challenged by terrestrial political tensions, could face additional strain if different nations interpret 3I Atlas effects differently or pursue conflicting strategies for managing interstellar contamination risks. The development of global protocols for responding to interstellar visitor encounters might become as complex and contentious as climate change negotiations, with similar implications for humanity's collective response to cosmic challenges. Perhaps most profoundly, the confirmation that interstellar visitors can meaningfully affect planetary environments would fundamentally alter humanity's understanding of our cosmic neighborhood. The universe would reveal itself as more dynamic and interconnected than our solar system-centric perspective had assumed, with implications that extend far beyond the immediate technical challenges of Mars exploration to encompass philosophical questions about cosmic citizenship and humanity's responsibilities as members of a galactic community we're only beginning to comprehend. In the quiet depths of this exploration, we must consider how the 3I Atlas encounter might reveal fundamental gaps in our understanding of planetary system dynamics that extend far beyond our current models of how celestial mechanics operate. The gravitational environment of our solar system, which we've come to view as a stable and predictable arrangement of planets, moons, and smaller bodies, might prove more susceptible to external influences than our Earth-centric experience has taught us to expect. The orbital resonances that maintain stability among Mars' moons, the asteroid belt objects, and even the broader planetary spacing could be sensitive to perturbations in ways that become apparent only when subjected to influences from outside our solar system's normal parameters. 3I Atlas carries momentum and gravitational potential that originated in stellar environments with different characteristics than our Sun, potentially introducing angular momentum or gravitational influences that don't perfectly align with the harmonic relationships that have stabilized over billions of years. These effects might manifest not as dramatic orbital changes, but as subtle shifts in resonance relationships that accumulate over long periods to create new patterns of celestial behavior. The asteroid belt, positioned between Mars and Jupiter, represents a particularly complex gravitational environment where small changes in orbital parameters can cascade through populations of objects over decades or centuries. Modifications to this region's dynamics could affect the long-term flux of asteroid material that occasionally threatens inner solar system planets, including Earth. The broader implications extend to our understanding of how planetary systems evolve and maintain stability over cosmic timescales. Current models of solar system formation and evolution assume that most significant perturbations come from within the system itself. Periodic orbital alignments, stellar mass loss as the Sun ages, or impacts from objects that originated within our solar system's gravitational sphere. The demonstration that interstellar visitors can introduce meaningful perturbations would require fundamental revisions to these models. Such revelations would affect not only our understanding of our own solar system's past and future, but also our interpretations of extrasolar planetary systems discovered around other stars. The stability and habitability of planets around distant suns might be more dependent on galactic environmental factors than we've previously considered, with implications for assessing the prevalence of life-supporting worlds throughout the galaxy. The deep structural integrity of Mars itself could face challenges from 3I Atlas that operate through mechanisms we're only beginning to understand. While the planet's surface appears geologically stable compared to Earth's dynamic tectonics, Mars harbors internal processes and structural vulnerabilities that could respond to external influences in unexpected ways. The planet's subsurface contains vast networks of ancient lava tubes, underground caverns, and fractured rock formations that resulted from billions of years of geological evolution, impact events, and thermal cycling. These subsurface structures exist in states of mechanical equilibrium that have persisted for millions of years. But equilibrium in geological systems often means that small external forces can trigger responses that propagate through underground networks in ways that eventually affect surface conditions. Gravitational influences from 3I Atlas, while minimal compared to the forces that shaped Mars' geological features, could potentially trigger subtle adjustments in subsurface stress patterns. These adjustments might manifest as minor seismic activity, changes in groundwater flow patterns, or modifications to the stability of underground cavern systems that future human explorers might depend on for shelter from radiation and atmospheric hazards. The planet's polar ice caps, composed of both water ice and frozen carbon dioxide, represent massive reservoirs of material that participate in Mars' seasonal cycles through sublimation and deposition processes. Changes to atmospheric conditions, electromagnetic environments, or thermal balances triggered by 3I Atlas could affect the stability of these ice deposits in ways that alter their contribution to atmospheric pressure variations and global climate patterns. Perhaps most concerning for future exploration efforts, the subsurface water ice that exists across much of Mars could prove sensitive to changes in electromagnetic or thermal environments. This frozen water represents the most accessible resource for supporting human life and fuel production on Mars. But its distribution and physical state depend on environmental conditions that have remained relatively stable for geological periods. Changes to these conditions could affect the reliability of resource extraction technologies that form the foundation of current Mars colonization planning. The permafrost layers that preserve organic compounds and geological records throughout Mars's subsurface could also respond to environmental changes in ways that affect scientific research objectives. These frozen layers contain the most promising locations for discovering evidence of past Martian life, but they also represent fragile archives that could be altered or destroyed by changes to thermal or chemical conditions. As our gentle journey through these cosmic possibilities continues, we encounter perhaps the most unsettling category of worst-case scenario, the possibility that 3I Atlas could trigger changes to Mars that operate through feedback mechanisms we don't fully understand, creating self-reinforcing processes that continue evolving long after the interstellar visitor has departed our solar system. Complex systems like planetary atmospheres and electromagnetic environments often exhibit nonlinear responses to external perturbations, where small initial changes can amplify through positive feedback loops to create outcomes that seem disproportionate to their original causes. Mars's climate system, while simpler than Earth's in many respects, still involves intricate interactions between atmospheric chemistry, surface thermal properties, polar ice dynamics, and dust particle behavior that could respond to 3I Atlas influences in unexpected ways. Consider how changes to atmospheric composition might affect the planet's dust cycle. Mars's famous dust storms depend on precise relationships between atmospheric heating, surface wind patterns, and the electrical properties of dust particles. If 3I Atlas introduces chemical compounds that alter how dust particles interact with each other or with electromagnetic fields, these changes could modify dust storm behavior in ways that create new patterns of atmospheric heating and cooling. Such modifications might establish new equilibrium states for Mars's climate system that persist indefinitely even after all direct traces of 3I Atlas influence have dissipated. The planet could essentially become locked into altered climate patterns that make it more or less suitable for human exploration than current conditions suggest. The electromagnetic feedback possibilities present equally complex scenarios. Changes to Mars's ionosphere or magnetic field interactions could affect how solar wind particles interact with the planet's upper atmosphere, potentially altering atmospheric loss rates or creating new patterns of charged particle circulation. These electromagnetic changes might interact with atmospheric chemistry modifications to create compound effects that neither influence would produce independently. Future Mars explorers might find themselves operating in environments that represent stable but altered states of planetary behavior, where the rules governing atmospheric dynamics, electromagnetic phenomena, and resource availability have been permanently modified by processes triggered during the 3I Atlas encounter, but sustained by internal planetary feedback mechanisms that continue operating according to their new parameters. The challenge for mission planners and planetary scientists lies in predicting which aspects of Mars's current behavior represent stable characteristics that will persist regardless of external influences, and which aspects might be susceptible to transitions toward alternative stable states that could fundamentally alter the planet's suitability for exploration and eventual human settlement. In the peaceful contemplation of these cosmic uncertainties, we must consider how the 3I Atlas encounter might create ripple effects that extend far beyond the immediate Mars system to influence the broader gravitational architecture of the inner solar system. The delicate orbital relationships that have maintained stability among the planets, their moons, and the populations of asteroids and comets represent a complex gravitational symphony that has played for billions of years with only minor variations. The introduction of an object with interstellar momentum and gravitational characteristics could create subtle perturbations that propagate through this system in ways that become significant over extended timescales. While 3I Atlas lacks the mass to directly alter planetary orbits, its passage through the inner solar system occurs at velocities and trajectories that don't align perfectly with the established gravitational harmonies that govern local celestial mechanics. These misalignments could introduce small but persistent changes to the orbital energies and angular momentum distributions of objects throughout the region, particularly affecting the populations of smaller bodies whose orbits are more sensitive to external influences. The main asteroid belt, positioned between Mars and Jupiter, contains thousands of objects whose orbital characteristics have been slowly evolving through gravitational interactions over millions of years. Even minute changes to this evolution could alter the long-term probability of asteroid impacts on inner planets. The Trojan asteroids that share Jupiter's orbit, the Apollo and Aten asteroids that cross Earth's orbital path, and the various comet populations that originate from the outer solar system all exist within gravitational environments that could be subtly influenced by 3I Atlas passage. These influences might manifest as gradual changes to orbital eccentricities, inclinations, or resonance relationships that accumulate over decades to create new patterns of object distribution throughout the inner solar system. Perhaps most concerning, these gravitational perturbations could affect the protective role that Jupiter plays in deflecting potentially hazardous objects away from the inner planets. Jupiter's massive gravitational influence acts as a cosmic vacuum cleaner that captures or redirects many objects that might otherwise threaten Earth and Mars. Changes to the orbital dynamics of objects in Jupiter's gravitational sphere could modify this protective effect in ways that increase the long-term impact risk for inner system planets. The biological implications of a worst-case 3I Atlas scenario extend into realms that challenge our fundamental assumptions about planetary protection and the preservation of environments for astrobiology research. Mars represents our most promising laboratory for understanding how life might develop and persist on worlds beyond Earth, but this scientific opportunity depends on maintaining the planet's environmental integrity for careful study. If 3I Atlas introduces biological contamination from interstellar sources, the implications could prove even more profound than chemical contamination. The possibility that interstellar objects might carry viable microorganisms or complex organic molecules that could influence planetary biospheres represents a category of cosmic risk that our current planetary protection protocols weren't designed to address. Microorganisms that evolved in stellar environments with different radiation characteristics, chemical compositions, or gravitational conditions might possess survival strategies that allow them to persist in Mars' harsh environment in ways that terrestrial life could not. Such organisms might establish themselves in Martian soil, subsurface water systems, or atmospheric chemistry cycles, creating permanent biological alterations to the planet's ecosystem. The detection and characterization of such alien biological activity would require analytical techniques that exceed our current capabilities. Distinguishing between indigenous Martian life signatures and contamination from interstellar sources might prove impossible with existing technology, potentially compromising decades of astrobiology research and undermining our understanding of how life develops on different worlds. Even more challenging, alien microorganisms might interact with indigenous Martian chemistry in ways that create hybrid biological systems that don't match any terrestrial models of how life operates. These interactions could accelerate chemical processes, alter atmospheric composition, or create biological cycles that persist long after the original contamination source has been removed. Future human missions to Mars would face unprecedented challenges in dealing with biological contamination, whose characteristics and behavior patterns remain unknown. Life support systems, food production technologies, and medical facilities would need protection against organisms whose metabolic processes, reproductive strategies, and potential pathogenicity have no terrestrial analogs for reference. The psychological impact on human explorers of discovering that Mars harbors alien biological activity could prove as challenging as the technical difficulties of operating in a contaminated environment. The knowledge that they're sharing the planet with life forms that originated around distant stars might fundamentally alter the human relationship with Mars exploration and colonization. As we drift through these deepening contemplations, the temporal scales of potential 3I Atlas effects reveal their most unsettling characteristics. Unlike the immediate consequences of impact events or atmospheric disruptions, the most significant long-term effects might unfold over timescales that exceed human planning horizons, creating challenges that persist for generations beyond those who initially encounter them. The half-lives of radioactive materials, the persistence of complex organic molecules in Mars' environment, and the stability of new equilibrium states in planetary systems all operate according to physical principles that measure time in decades, centuries, or millennia, rather than the years or decades that characterize human technological development and institutional memory. Future human settlements on Mars might inherit environmental conditions that reflect modifications triggered by 3I Atlas, but the settlers themselves might have no direct knowledge of the original cause of these conditions. They would be forced to develop technologies and survival strategies based on environmental parameters that don't match historical records or theoretical models, potentially struggling with challenges whose origins have been forgotten by the institutions that originally documented the interstellar encounter. The intergenerational aspects of these scenarios raise profound questions about humanity's responsibility to preserve accurate records and analytical capabilities that might be needed decades or centuries in the future. Current scientific institutions, government agencies, and international agreements operate on timescales that rarely extend beyond a few decades, yet the consequences of cosmic encounters might require sustained observation and analysis efforts that span multiple centuries. Climate systems, ecological relationships, and geological processes all exhibit memory effects where current conditions reflect the influence of events that occurred far in the past. If 3I Atlas creates lasting changes to Mars's environmental systems, these changes might continue influencing planetary conditions long after all direct evidence of the original encounter has disappeared. Future planetary scientists might find themselves studying environmental phenomena on Mars that they can't fully explain because the causal events occurred before their analytical frameworks were developed. They might develop theories and models based on incomplete information, leading to technological and strategic decisions that prove inadequate for environments whose characteristics they don't completely understand. The preservation of institutional knowledge across these extended timescales represents a challenge that human civilization has rarely faced successfully. Most of our experience with long-term information preservation involves passive storage of historical records, but managing the consequences of cosmic encounters might require active monitoring and analysis programs that maintain continuity across multiple generations of technological and social change. In the gentle quietude of our exploration, we must consider how the 3I Atlas encounter might reveal the interconnected nature of cosmic systems in ways that challenge our compartmentalized approach to studying individual planets and celestial objects. The solar system operates as an integrated network of gravitational, electromagnetic, and chemical relationships where changes in one region can influence conditions throughout the entire system over extended periods. Mars exists within this cosmic web not as an isolated world, but as a participant in complex cycles that involve the exchange of material and energy between planets, moons, asteroids, and the interplanetary medium. Dust particles launched from Mars by impact events eventually spread throughout the inner solar system, contributing to the cosmic dust environment that affects spacecraft operations and planetary atmospheric interactions. Changes to Mars' dust production or atmospheric chemistry could influence conditions on Earth, Venus, and other bodies over geological timescales. The solar wind that streams continuously outward from our Sun creates a dynamic medium through which all planets move, carrying charged particles and electromagnetic fields that interact with planetary magnetospheres and atmospheres in ways that vary depending on solar activity cycles and local magnetic field configurations. Modifications to how Mars interacts with the solar wind, triggered by 3I Atlas influences, could create electromagnetic disturbances that propagate throughout the inner solar system. These systemic effects might prove most significant for understanding how planetary systems respond to external perturbations over cosmic timescales. The stability and habitability of worlds around other stars could be more dependent on galactic environmental factors than we've previously recognized, with implications for assessing the prevalence and persistence of life-supporting conditions throughout the galaxy. Our current models of solar system evolution assume that most significant changes result from internal processes or predictable external influences, like stellar evolution or periodic comet impacts from within our solar system's gravitational sphere. The demonstration that interstellar visitors can introduce meaningful perturbations would require fundamental revisions to these models, with implications for understanding how planetary systems develop and maintain habitability over billions of years. The revelation that cosmic systems exhibit this level of interconnectedness might also influence how we approach the search for life around other stars, suggesting that the habitability of distant worlds depends not only on their individual characteristics, but also on the galactic environments through which their stellar systems move over cosmic time. The deepest philosophical implications of a worst-case 3I Atlas scenario perhaps lie in how such an encounter might transform humanity's understanding of our cosmic responsibilities and our relationship with the universe itself. The recognition that interstellar visitors can meaningfully affect planetary environments would fundamentally alter our conception of Earth and Mars as isolated worlds that develop according to their own internal dynamics. This shift in perspective could prove as significant as the Copernican revolution that displaced Earth from the center of the universe, or the discovery of deep time that revealed the vast scales on which geological and biological processes operate. The realization that planetary environments exist within galactic ecosystems where objects from distant stellar systems can influence local conditions would require reconceptualizing our place in cosmic hierarchies of scale and influence. The implications extend beyond academic astronomy to encompass practical questions about planetary stewardship and the ethics of space exploration. If planets can be influenced by visitors from other stellar systems, humanity's responsibilities as cosmic citizens might extend beyond protecting worlds within our solar system to considering how our own activities might affect the broader galactic environment through which we move. Future space exploration efforts might need to account for the possibility that our spacecraft and technological activities could influence interstellar objects or cosmic processes in ways that eventually affect other stellar systems. The rockets we launch, the radio signals we broadcast, and the materials we distribute throughout space all become part of the galactic environment that interstellar visitors encounter during their journeys between stars. These considerations might influence how we approach the development of interstellar travel technologies and the protocols we establish for eventual contact with extraterrestrial civilizations. The knowledge that cosmic systems exhibit complex interconnections across vast scales suggests that advanced civilizations might need to develop sophisticated frameworks for managing their galactic environmental impact. The psychological and cultural implications of recognizing our embedded position within galactic-scale systems could prove as transformative as the immediate technical challenges of managing 3I Atlas effects on Mars exploration. Human civilization might be forced to develop new categories of environmental ethics that encompass our responsibilities to cosmic systems whose scales exceed terrestrial experience. Such expanded awareness might also influence how we interpret our relationship with Earth's environment, suggesting that planetary stewardship requires understanding connections and influences that extend far beyond the boundaries of individual worlds. As our contemplation continues through these cosmic depths, the question of detection and monitoring capabilities reveals perhaps the most practical immediate challenge posed by worst-case 3I Atlas scenarios. Our current ability to observe and understand interstellar objects remains limited by technological constraints and theoretical frameworks that were developed for studying objects within our solar system. The instruments and analytical techniques that have proved successful for characterizing solar system comets, asteroids, and planetary environments might prove inadequate for detecting and interpreting the subtle effects that interstellar visitors could have on planetary systems. The chemical signatures, electromagnetic phenomena, and gravitational influences associated with objects from other stellar systems might require entirely new categories of measurement and analysis that exceed our current capabilities. The temporal aspects of these detection challenges prove particularly daunting. Many of the most significant effects we've been exploring would unfold over periods measured in years, decades, or centuries, requiring sustained observation programs that maintain continuity across multiple generations of scientific and technological development. Current space missions typically operate for periods measured in years or decades, with funding and institutional support that rarely extends beyond the careers of individual researchers or the strategic planning horizons of government agencies. The development of monitoring systems capable of detecting and characterizing long-term changes to planetary environments would require unprecedented levels of international cooperation and institutional commitment. Such systems would need to maintain operational continuity across political changes, technological evolution, and shifts in scientific priorities that could easily disrupt observation programs before they accumulate sufficient data to detect subtle but significant trends. The challenge becomes even more complex when considering that the most important effects might be those we haven't yet learned to recognize or measure. The scientific frameworks and theoretical models that guide current observation strategies were developed based on experience with solar system objects and processes. Interstellar visitors might introduce phenomena that fall outside these frameworks, requiring the development of new analytical approaches that could take decades to mature. Future generations of researchers might look back at our current 3I Atlas observations and recognize crucial information that we missed because we lacked the conceptual tools or measurement techniques needed to detect and interpret interstellar influences on planetary systems. The data we're collecting today might contain signatures of cosmic processes that won't be understood until theoretical advances provide the context needed for proper interpretation. The quantum mechanical implications of a worst-case 3I Atlas encounter introduce us to realms where cosmic-scale events intersect with the fundamental structures of matter and energy in ways that challenge our understanding of how physical processes operate across vastly different scales. At the deepest levels of reality, where particles and fields interact according to quantum mechanical principles, the introduction of matter and energy from alien stellar environments could create subtle but persistent modifications to the quantum vacuum fluctuations and field interactions that underlie all physical phenomena. Consider how the exotic nuclear isotopes and complex molecular structures that 3I Atlas carries from its distant origin might possess quantum mechanical properties that differ from anything that has existed in our solar system since its formation. These differences could manifest as variations in nuclear decay rates, alterations to atomic emission spectra, or modifications to the way matter interacts with electromagnetic fields at the quantum level. Such changes would be extraordinarily subtle, detectable only through precision measurements, using the most sophisticated atomic clocks and quantum sensors available to modern physics. The implications extend beyond academic physics to encompass practical consequences for technologies that depend on precise quantum mechanical phenomena. Global positioning systems rely on atomic clocks, whose accuracy depends on stable nuclear decay rates and atomic transition frequencies. Communication systems use quantum properties of semiconductors and crystalline structures that could be influenced by the presence of exotic matter with different quantum characteristics. Even the chemical processes that govern atmospheric chemistry and biological metabolism operate according to quantum mechanical principles, that could be subtly modified by the introduction of matter that evolved under different stellar conditions. The persistence of these quantum mechanical effects presents particularly intriguing possibilities. Unlike macroscopic physical changes that might fade over time as planetary systems return to equilibrium, quantum mechanical modifications could become permanently integrated into the fundamental physical processes that govern how matter and energy behave in the affected regions. Future scientists studying Mars might discover that certain atomic transition frequencies differ slightly from terrestrial measurements, or that radioactive decay rates exhibit anomalies that can't be explained by conventional nuclear physics models. These quantum effects might also interact with Mars's geological processes in ways that create long-term modifications to the planet's physical properties. Crystalline structures in rocks and minerals might incorporate alien isotopes that alter their thermal conductivity, magnetic properties, or mechanical strength in ways that become apparent only when future colonists attempt to use Martian materials for construction or resource extraction. The precision manufacturing and nanotechnology applications that advanced human settlements would require might need to account for quantum mechanical properties of Martian matter that differ from terrestrial norms. Perhaps most profound would be the discovery that quantum mechanical processes themselves might serve as carriers of information about cosmic history, preserving details about the stellar environments where exotic matter originated in ways that could be decoded by sufficiently advanced analytical techniques. The quantum states of atoms and molecules might retain signatures of the gravitational fields, radiation environments, and electromagnetic conditions that existed around distant stars billions of years ago, creating a kind of quantum archaeological record that tells stories about stellar evolution and planetary formation processes that occurred in regions of the galaxy we can never directly observe. The detection and study of such quantum mechanical effects would require developing new categories of precision measurement that exceed current technological capabilities by orders of magnitude. Future Mars missions might need to include quantum laboratories equipped with atomic interferometers, precision spectroscopy equipment, and quantum sensors that can detect variations in fundamental physical constants at levels of sensitivity that push the boundaries of what's theoretically possible with any conceivable technology. As we venture deeper into the cosmic implications of potential 3I Atlas effects, the thermodynamic consequences of introducing matter and energy from alien stellar environments begin to reveal their subtle but potentially transformative influence on planetary energy systems. Mars operates according to thermal equilibrium principles that balance incoming solar radiation with outgoing thermal emission, creating temperature gradients and energy flows that drive atmospheric circulation, geological processes, and the cycling of volatile materials between different planetary reservoirs. The introduction of exotic materials with thermal properties that differ from anything in our solar system's inventory could create persistent modifications to these energy balance equations. Consider how the complex organic molecules and unusual crystalline structures that 3I Atlas might deposit could possess thermal absorption and emission characteristics that operate outside the parameters of current climate models. These materials might absorb solar radiation at wavelengths where Mars's atmosphere is normally transparent, or emit thermal radiation in spectral bands that don't match the planet's current energy budget calculations. Such changes could trigger cascading modifications to Mars's thermal behavior that persist long after the direct influence of 3I Atlas has dissipated. Local regions where alien materials accumulate might develop different heating and cooling rates than surrounding areas, creating temperature gradients that drive new patterns of atmospheric circulation. These circulation changes could redistribute dust, water vapor, and thermal energy in ways that establish new equilibrium states for regional or global climate systems. The subsurface thermal environment could prove particularly sensitive to these influences. Mars's interior retains heat from its formation and from radioactive decay processes that have operated for billions of years, creating temperature gradients that influence groundwater behavior, permafrost stability, and the potential for subsurface biological activity. Exotic radioactive isotopes introduced by 3I Atlas might alter these internal heat sources in ways that modify subsurface temperature profiles over geological timescales. The implications for future resource extraction and habitat construction could prove significant. Human settlements on Mars would depend on understanding and utilizing the planet's thermal environment for heating, cooling, and energy generation systems. Power systems based on thermal differential engines, geothermal energy extraction, or radioisotope, thermal generators might encounter thermal conditions that differ from current models in ways that affect their efficiency or operational lifetimes. Perhaps most intriguingly, the thermodynamic modifications introduced by 3I Atlas could create opportunities for entirely new categories of energy technology, based on exploiting thermal properties that don't exist naturally in our solar system. Future Mars colonists might discover that certain combinations of alien and native materials exhibit thermal behaviors that enable more efficient energy storage, heat transfer, or thermal conversion processes than anything achievable with purely terrestrial technology. The study of these thermodynamic effects would require developing new theoretical frameworks that can predict how materials with exotic thermal properties interact with planetary energy systems over extended timescales. Current climate models assume that thermal parameters remain constant over the periods relevant to human planning, but the introduction of alien materials could invalidate these assumptions in ways that require fundamental revisions to how we understand planetary energy balance and climate stability. The ecological implications of a worst-case 3I Atlas scenario extend into realms that challenge our fundamental understanding of how life adapts to changing environmental conditions and how ecosystems respond to the introduction of entirely novel chemical and physical parameters. While Mars currently lacks any confirmed biological activity, the planet harbors environmental conditions that could potentially support certain categories of extremophile organisms, and future human settlements would inevitably introduce terrestrial biology to Martian environments in ways that create new ecological systems. The chemical modifications that 3I Atlas might introduce to Mars's environment could prove particularly significant for understanding how biological systems respond to exposure to matter that evolved under completely different stellar conditions. Terrestrial life has evolved biochemical processes that are optimized for the specific chemical environment that exists on Earth, including the particular isotopic ratios, trace element concentrations, and molecular structures that characterize our planet's biosphere. Organisms transported to Mars as part of human exploration and settlement. Efforts would encounter not only the challenging baseline conditions of reduced atmospheric pressure, lower temperatures, and high radiation levels, but potentially also chemical environments modified by the presence of exotic compounds that have no terrestrial analogs. The metabolic pathways, cellular repair mechanisms, and reproductive processes that enable life to function on Earth might prove inadequate for environments that include chemical components that didn't participate in the evolutionary processes that shaped terrestrial biology. These effects could manifest in ways that range from subtle modifications to biological efficiency to more dramatic failures of fundamental life support processes. Plants grown in Martian soil that has been chemically modified by 3I Atlas materials might exhibit altered growth rates, changed nutritional content, or modified resistance to environmental stresses. Microorganisms responsible for waste processing, food production, and atmospheric regulation in closed ecological systems might experience changes to their metabolic efficiency or genetic stability when exposed to exotic chemical environments. The longer-term evolutionary implications could prove even more profound. Biological systems possess remarkable abilities to adapt to environmental changes through genetic modification and selective pressure. But these adaptation mechanisms operate according to principles that assume environmental parameters remain within ranges that have existed throughout Earth's biological history. The introduction of completely novel chemical and physical conditions could drive evolutionary processes in directions that have no precedent in terrestrial biology. Future Mars ecosystems might develop along evolutionary pathways that produce organisms with biochemical properties, ecological relationships, and physiological capabilities that differ fundamentally from anything that has existed on Earth. These evolutionary modifications could prove beneficial, creating biological systems that are better adapted to Martian conditions than purely terrestrial organisms, or they could prove problematic, leading to ecological instabilities or failures that compromise the viability of human settlements. The management of these ecological challenges would require developing entirely new disciplines that combine astrobiology, evolutionary biology, and ecological engineering in ways that can predict and guide biological adaptation to environments that include components from other stellar systems. Future Mars settlements might need to maintain sophisticated biological monitoring and genetic analysis capabilities that can detect and respond to evolutionary changes as they occur, rather than simply assuming that terrestrial biological systems will continue operating according to Earth-based parameters. The information and computational aspects of managing a worst-case 3I Atlas scenario reveal perhaps the most practically challenging dimensions of how human civilization might need to adapt to cosmic events that exceed our current analytical and technological capabilities. The data processing requirements for understanding and responding to interstellar contamination events would strain our current computational infrastructure and require developing new categories of analysis that combine astronomical observation, planetary science, and environmental monitoring at scales and timescales that exceed any previous scientific undertaking. Consider the sheer volume of information that would need to be collected, processed, and interpreted to understand how exotic materials from 3I Atlas might be affecting Mars's environmental systems. Current Mars missions generate terabytes of data annually through spacecraft observations, rover measurements, and orbital surveys. But this information flow assumes relatively stable planetary conditions that can be characterized through established analytical frameworks. The introduction of unknown variables from interstellar sources would multiply the data collection requirements by orders of magnitude while simultaneously requiring the development of entirely new theoretical models for interpreting observations. The temporal aspects of this information challenge prove particularly daunting. Many of the most significant effects we've been exploring would unfold over periods measured in decades or centuries, requiring sustained data collection and analysis programs that maintain consistency and continuity across multiple generations of technological evolution. Current computing architectures, data storage systems, and analytical algorithms might prove inadequate for processing information flows that continue accumulating for decades, while simultaneously requiring increasingly sophisticated analysis techniques as our understanding of interstellar contamination effects evolves. The artificial intelligence and machine learning systems that would be essential for detecting subtle patterns in vast datasets, spanning multiple decades, would need to operate according to principles that account for the possibility that the underlying physical and chemical processes being monitored might be changing in ways that invalidate previous training data. Traditional machine learning approaches assume that past patterns provide reliable guidance for interpreting future observations. But interstellar contamination events could introduce variables that make historical data misleading or irrelevant for understanding current conditions. Future Mars settlements would need to maintain computational capabilities that can adapt to changing environmental parameters while simultaneously preserving the analytical consistency needed to detect long-term trends. This would require developing computing architectures that combine massive parallel processing capabilities with adaptive algorithms that can recognize when fundamental assumptions about planetary behavior need revision. The settlement's survival might depend on computational systems that can distinguish between normal environmental variation and potentially dangerous changes triggered by ongoing interstellar contamination effects. The communication challenges associated with managing these information flows across interplanetary distances would add another layer of complexity to an already overwhelming technical challenge. The time delays inherent in Earth-Mars communication mean that critical analytical processing might need to occur locally on Mars, requiring settlements to maintain scientific and computational capabilities that can operate independently of Earth-based support for extended periods. The bandwidth limitations of interplanetary communication would require developing data compression and prioritization algorithms that can identify the most crucial information for transmission while preserving sufficient detail for Earth-based researchers to contribute to ongoing analysis efforts. Perhaps most challenging would be the requirement to maintain these information processing capabilities across institutional and technological transitions that could disrupt continuity in ways that compromise long-term monitoring programs. The political, economic, and technological changes that occur over decades could easily interrupt data collection or analysis programs before they accumulate sufficient information to detect and characterize subtle but significant environmental changes. Future information management systems would need to be designed with redundancy and institutional independence that can survive changes in government priorities, funding allocations, and technological paradigms. The materials science implications of a worst-case 3-eye atlas encounter extend into realms where the fundamental properties of matter itself might be modified by exposure to substances that evolved under stellar conditions, completely unlike those that shape the formation of materials in our solar system. The crystalline structures, molecular bonds, and atomic arrangements that determine how materials behave under various conditions of temperature, pressure, and electromagnetic exposure could prove sensitive to the presence of exotic atoms and molecules that carry the signatures of alien stellar environments. Consider how the construction materials that future Mars settlements would depend on might interact with trace amounts of interstellar contamination in ways that alter their mechanical properties, chemical stability, or electromagnetic characteristics over extended periods. The metals extracted from Martian ores, the ceramics produced from processed regolith, and the composite materials manufactured from local resources might develop unexpected brittleness, corrosion patterns, or thermal expansion behaviors when exposed to chemical environments that include components not found in terrestrial materials, science databases. These effects could prove particularly significant for the life support systems and habitat structures that would be essential for human survival on Mars. The seals, filters, and barrier materials that maintain atmospheric pressure and composition in habitable environments might experience accelerated degradation or unexpected failure modes when exposed to exotic chemical compounds that interact with polymers, metals, and ceramics in ways that have no terrestrial analogs. The failure of critical life support components due to materials interactions that couldn't be predicted from Earth-based testing could pose immediate threats to human safety. The manufacturing processes that Mars settlements would use to produce tools, equipment, and infrastructure from local resources might also be affected by the presence of interstellar contamination in ways that require fundamental modifications to industrial techniques. The chemical processes used for metal refining, ceramic production, and polymer synthesis all assume specific chemical environments and material properties that could be altered by the presence of exotic atoms or molecules. Manufacturing systems might need to incorporate purification stages or compensation mechanisms that account for the modified properties of contaminated raw materials. Perhaps most intriguingly, the presence of materials with properties that don't exist naturally in our solar system might create opportunities for developing entirely new categories of technology based on exploiting characteristics that result from the interaction between terrestrial and interstellar matter. Future Mars colonists might discover that certain combinations of Earth-derived and alien-contaminated materials exhibit superior strength, conductivity, or chemical resistance compared to purely terrestrial substances. The development of quality control and testing protocols for materials that might contain unknown levels of interstellar contamination would require advancing materials, science, analytical techniques beyond their current capabilities. Future Mars settlements would need to maintain sophisticated laboratory facilities that can characterize material properties at the atomic level and detect trace contamination levels that might affect performance over the decades-long operational lifetimes required for critical infrastructure components. The implications extend beyond immediate practical concerns to encompass fundamental questions about how materials science knowledge developed on Earth might need modification when applied to environments that include components from other stellar systems. The periodic table of elements remains universal, but the specific isotopic ratios, molecular structures, and crystalline arrangements that determine material properties could vary in ways that require developing new theoretical frameworks for predicting how matter behaves under conditions that have no terrestrial precedent. As our contemplation approaches its deeper philosophical dimensions, the consciousness and cognitive implications of exposure to a universe revealed as more dynamic and interconnected than previously understood begin to emerge as perhaps the most profound category of consequence that could result from a worst-case 3I Atlas scenario. The psychological adaptation required for human beings to function effectively in environments where fundamental assumptions about planetary stability and cosmic predictability have been challenged could prove as demanding as the technical challenges of operating in altered physical conditions. Human consciousness evolved within terrestrial environments that exhibit certain patterns of stability, predictability, and cause and effect relationships that have shaped not only our cognitive processes, but also our deepest assumptions about how reality operates. The discovery that planetary environments can be significantly altered by visitors from other stellar systems would challenge these fundamental cognitive frameworks in ways that could require generations of psychological and cultural adaptation. Future Mars colonists might need to develop entirely new categories of mental resilience and adaptive flexibility that allow them to function effectively in environments where basic assumptions about physical reality might be continuously subject to revision. The stress of living with ongoing uncertainty about environmental stability could manifest in ways that affect both individual psychology and social dynamics within Mars settlements. The knowledge that the air, water, soil, and electromagnetic environment might be undergoing gradual changes triggered by interstellar contamination could create persistent low-level anxiety that affects decision-making, risk assessment, and long-term planning capabilities. Colonists might develop heightened sensitivity to environmental changes that could prove either adaptive or maladaptive, depending on whether their concerns reflect genuine threats or psychological amplification of natural variations. The intergenerational transmission of knowledge and cultural adaptation strategies would become particularly crucial for communities that must maintain operational effectiveness across decades during which environmental conditions might be slowly evolving in ways that aren't immediately obvious. Children born on Mars might need to develop cognitive frameworks that treat environmental uncertainty as a normal condition rather than an exceptional crisis, requiring educational approaches that prepare them for lifetimes of adaptive problem-solving in conditions that exceed their parents' experience. The social and political implications of managing communities under conditions of ongoing environmental uncertainty could prove equally challenging. Democratic decision-making processes, economic planning systems, and social institutions all assume certain levels of predictability that allow for long-term planning and resource allocation. Communities that must continuously adapt to potentially changing environmental conditions might need to develop more flexible and responsive governance structures that can make rapid adjustments to policies and priorities based on emerging environmental data. The cultural and spiritual dimensions of human adaptation to cosmic citizenship represent perhaps the most profound aspect of this psychological transition. The recognition that human settlements exist within galactic systems, where events occurring around distant stars can influence local environmental conditions, might require developing new categories of meaning-making and identity formation that encompass cosmic scales of connection and responsibility. Future Mars colonists might need to develop cultural frameworks that help them maintain psychological stability and community cohesion, while simultaneously acknowledging their embedded position within cosmic systems whose behavior exceeds human control or complete understanding. The preservation of psychological resilience across the extended timescales required for adapting to gradually changing environmental conditions would require developing new approaches to mental health support and community psychology that account for the unique stresses of living in environments where fundamental assumptions about reality stability might be subject to ongoing revision. Future space psychology might need to incorporate elements of philosophy, cosmology, and systems thinking that help individuals and communities maintain functional perspectives on their place within cosmic systems that operate according to scales and principles that challenge human comprehension. The synthesis of all these potential consequences reveals that a worst-case 3-eye Atlas scenario might ultimately serve as humanity's introduction to the true complexity of galactic citizenship, where our species must learn to function within cosmic systems that operate according to principles and timescales that exceed terrestrial experience and challenge fundamental assumptions about predictability, control, and environmental stability. This transition from a solar system-centric civilization to one that acknowledges its embedded position within galactic-scale processes might prove as transformative as any previous revolution in human understanding of our cosmic context. The cumulative effects of quantum mechanical modifications, thermodynamic alterations, ecological disruptions, materials, science challenges, informational processing requirements, and psychological adaptations would create a cascade of interconnected changes that exceed the sum of their individual impacts. Future Mars settlements might find themselves operating within environmental and technological contexts that require continuous adaptation and innovation at rates that challenge human institutional and cognitive capabilities. The traditional approach of developing comprehensive understanding before implementing solutions might prove inadequate for managing systems that continue evolving faster than analysis can characterize their behavior. The development of adaptive resilience rather than predictive control might become the defining characteristic of successful human expansion into cosmic environments where interstellar influences can introduce variables that exceed our analytical capabilities. Rather than attempting to achieve complete understanding and control of environmental systems, future space civilizations might need to prioritize flexibility, redundancy, and rapid response capabilities that allow them to function effectively, even when operating under conditions of fundamental uncertainty about system behavior and long-term trends. The institutional innovations required for managing these challenges would likely transcend current models of scientific research, technological development, and social organization. The timescales involved in monitoring and responding to interstellar contamination effects would require developing new forms of institutional continuity that can maintain operational effectiveness across multiple generations of political, economic, and technological change. These institutions would need to balance the requirements for long-term consistency with the need for adaptive flexibility that allows them to respond to emerging challenges and opportunities that couldn't be anticipated when they were originally established. The educational and cultural adaptations necessary for preparing humans to function effectively as cosmic citizens would require fundamental revisions to how we conceptualize knowledge, expertise, and decision-making under conditions of irreducible uncertainty. Future educational systems might need to emphasize adaptive problem-solving, systems thinking, and psychological resilience rather than the acquisition of specific technical knowledge that might become obsolete as environmental conditions evolve. The cultivation of intellectual humility and comfort with uncertainty might become as important as traditional technical skills for individuals who must function in environments where the basic parameters of physical reality might be subject to ongoing modification. The philosophical implications of acknowledging our embedded position within galactic systems that include regular interstellar visitors would require developing new frameworks for understanding human agency, responsibility, and meaning within cosmic contexts that operate according to scales that dwarf individual and even civilizational lifespans. The recognition that our local environment can be influenced by events that occurred around distant stars millions of years ago, and that our own activities might eventually influence conditions around stars we'll never see, would require expanding our conception of moral responsibility and causal connection to encompass cosmic scales that challenge human intuition and emotional comprehension. As we approach the gentle conclusion of our cosmic contemplation, the integration of these various worst-case scenarios into a coherent understanding reveals that the Three-Eye Atlas encounter, regardless of its specific outcomes, serves as a profound reminder of the dynamic nature of cosmic systems and the ongoing challenges that face any civilization attempting to expand beyond its planetary origins. The universe operates according to principles that often transcend the scales of time, space, and complexity that characterize human experience, creating conditions where even the most sophisticated planning and preparation might prove inadequate for managing cosmic encounters that introduce variables beyond our current comprehension. The peaceful acceptance of this cosmic uncertainty might ultimately prove more valuable than specific technical solutions to particular challenges. The recognition that we exist within systems whose behavior exceeds our complete understanding or control could foster the development of wisdom traditions and cultural frameworks that emphasize adaptation, resilience, and humble recognition of our limitations, rather than the illusion of comprehensive mastery over our environment. This shift in perspective might prove essential for the psychological and spiritual health of spacefaring civilizations that must function effectively while acknowledging their embedded position within cosmic systems that operate according to principles they can influence but never fully control. The legacy of the 3I Atlas encounter might ultimately be measured not by its immediate effects on Mars exploration or technological development, but by its contribution to humanity's maturation as a cosmic civilization capable of functioning within galactic systems while maintaining psychological stability and cultural continuity across the extended timescales required for space expansion. The gentle wisdom of accepting uncertainty while maintaining operational effectiveness might become a defining characteristic of successful space civilizations, allowing them to pursue ambitious goals while remaining psychologically prepared for outcomes that exceed their predictions and capabilities. The development of cosmic humility might prove as important as technological advancement for civilizations that must function within galactic environments, where interstellar visitors regularly introduce variables that challenge local understanding and adaptation capabilities. The cultivation of mental frameworks that can maintain functional optimism and operational effectiveness while simultaneously acknowledging the fundamental limitations of predictive control might become essential survival skills for spacefaring species. The peaceful contemplation of these cosmic challenges during quiet moments like this, when the mind can explore complex possibilities without the pressure of immediate decision-making requirements, might prove essential for developing the psychological resilience and intellectual flexibility required for cosmic citizenship. The ability to consider vast scales and complex scenarios while maintaining emotional equilibrium and practical focus represents a form of mental training that could prove as valuable as technical education for individuals who must function in environments where the basic parameters of reality might be subject to ongoing modification by cosmic forces beyond their immediate influence. The recognition that even worst-case scenarios can serve as opportunities for growth, adaptation, and the development of previously unimagined capabilities might ultimately prove more valuable than specific predictions about what 3I Atlas might or might not do to Mars. The universe consistently demonstrates that its creative potential exceeds our ability to predict specific outcomes, while simultaneously providing the challenges and opportunities necessary for the development of increased wisdom, capability, and cosmic consciousness. In the tranquil depths of this final contemplation, we return to the essential recognition that the universe operates as an integrated system of relationships and influences that extend far beyond the boundaries of individual planets, stellar systems, or even galaxies. The 3I Atlas encounter, whether it produces dramatic changes to Mars or passes with minimal observable effects, serves as a gentle reminder that our existence unfolds within cosmic contexts that regularly introduce elements of surprise, challenge, and opportunity that exceed our predictive capabilities, while simultaneously providing the conditions necessary for continued growth and development. The worst-case scenarios we've explored tonight represent not prophecies of doom, but invitations to expand our understanding of the complexity and interconnectedness that characterize cosmic systems at all scales. Each potential challenge reveals opportunities for developing increased resilience, deeper wisdom, and more sophisticated approaches to functioning within environments that operate according to principles that transcend human control while remaining responsive to human creativity, adaptation, and collaborative problem-solving capabilities. The peaceful exploration of these possibilities during quiet contemplative moments creates mental and emotional preparation for whatever cosmic encounters the future might bring, while simultaneously fostering the psychological flexibility and intellectual humility that prove essential for maintaining well-being and operational effectiveness under conditions of fundamental uncertainty. The cultivation of comfort with mystery and change, combined with confidence in human adaptive capabilities, might ultimately prove more valuable than specific technical preparations for particular scenarios. As 3i Atlas continues its ancient journey through our solar system, carrying within its nucleus the chemical signatures of stellar environments we can barely imagine, it serves as a cosmic messenger reminding us that we participate in galactic systems that operate according to principles of beauty, complexity, and interconnection that exceed our complete comprehension while remaining fundamentally hospitable to consciousness, creativity, and the ongoing evolution of intelligence and wisdom. The gentle dance between Mars and its interstellar visitor unfolds according to gravitational and electromagnetic principles that have operated for billions of years, creating conditions where even the most dramatic potential changes occur within contexts of cosmic stability and continuity that have supported the development of complexity, consciousness, and civilization throughout the observable universe. Whatever specific effects emerge from this encounter, they occur within cosmic systems that have consistently demonstrated their capacity to support the ongoing development of intelligence, creativity, and wisdom across vast scales of space and time. In the peaceful silence that follows these contemplations, we can rest in the recognition that we exist within a universe that combines challenge and support, mystery and comprehensibility, change and continuity in ways that create optimal conditions for continued growth, discovery, and the expansion of consciousness into ever more sophisticated relationships with cosmic systems that exceed our current understanding while remaining fundamentally responsive to intelligence, creativity, and the sincere desire to contribute positively to the ongoing evolution of complexity and beauty throughout the cosmos. The story of 3i Atlas and Mars continues to unfold in the gentle rhythms of orbital mechanics and cosmic time, reminding us that we participate in narratives that extend far beyond individual lifespans while remaining intimately connected to our immediate experience of wonder, curiosity, and peaceful contemplation of the magnificent complexity that surrounds and includes us in each moment of conscious awareness.